Thank you.
I have got entire classes not filmed here because that error pops up. So I have two electric fields involved here. I've got the electric fields from the plates, and then I have electric field from the dielectric, and if I combine them, I get a lower electric field. But the relationship that was written over there, the fact that the potential difference is equal to the negative electric field times the distance, actually, mathematically, that is just awkward. That's more accurate. So this holds true. So if my electric field gets smaller, well, my voltage would get smaller. Assuming that I have it fixed. Or, so if I have, let me be a little bit more specific here. I have a capacitor that I charge up. Take the scenario over there. Get it all charged up. Now what I want to do is I'm going to break the connection. When I break the connection, if I can do it fast enough, then the charge on here will stay fixed. If I don't have a current, don't have a circuit anymore, then what's going to happen is that the charge has no place to go, so the charge stays fixed. I then add a dielectric to it, which lowers my electric field to keep the distance the same, and so my voltage will change. My voltage will get smaller. Well, if my voltage is smaller, but my charge stays the same, what happens to my capacitance? Charge stays the same, voltage gets smaller.
The bigger number.
Pardon?
Yeah, the bigger number than before.
Yeah, you increase the capacitance. So what a dielectric does ultimately is to increase the capacitance of a capacitor. Actually, it does two things. One, it does increase the capacitance by itself, but also if I put an insulator between the two plates, that means I can get the plates closer together. I can smash them together so that the distance between them, D, is whatever the thickness of the dielectric is, and in one lap, it'll be a piece of paper or several pieces of paper. So I can increase the capacitance by decreasing this and by changing that ratio. All this is well and good. Let's throw some numbers into it. So what I'm going to do is I'm going to take this capacitor over here, set up. I'm going to keep it connected to the battery. So just a quick tip. If battery stays connected, voltage across the capacitor is fixed. If the battery is disconnected, and we will assume that the disconnection of the battery is done ideally. If battery is disconnected, charge on the capacitor is fixed. Reality check here. If I actually disconnect it, I got a charge build up here. If I'm disconnecting the capacitor from the battery, there's enough charge on here that potentially it's going to spark. And if it sparks, you're losing charge. So that's why when you disconnect it, you have to disconnect it fast enough so that there's no spark. We do not have the capability of disconnecting fast enough. I've tried. I don't have the capacity to disconnect it fast enough. so I'm gonna take that over there and I'm keeping it connected to the battery, and I'm gonna add a dielectric Now, this right here is known as the dielectric constant. It is constant for the dielectric, it's not the universal constant that it's not always 2. If I have a specific material, it has a specific dielectric, so this is the dielectric constant, not to be confused with the dielectric strength, which is how much voltage can I crank up before a hole gets burned through the dielectric. So dielectric constant. Now, what is the dielectric constant? Well, if I'm dealing with a dielectric, this 8.85 times 10 to the negative 12 is the permittivity of free space. So if I got nothing in between the capacitors at all, that's the dielectric. This is the permittivity you would use. As I put in the dielectric, this doesn't quite cut it anymore. That the permittivity of the dielectric, of the dielectric is equal to epsilon. Now, because of the number of digits usually involved in epsilon, they thought, you know what, let's come up with something simpler. So they decided if you take the permittivity of a dielectric and you divide by the smallest value it can be, that is equal to the dielectric constant. Now, it might look like I'm drawing the letter K. This is actually a kappa. Which look a lot like my K's. Put extra curls in it. That creates a kappa. So my capacitance, Q over delta V, equal to, well, I just can't get away with epsilon sub naught anymore because I am dealing with the dielectric. And so what I do is I just multiply times the kappa epsilon sub naught, A over D. Or if you prefer, epsilon A. This is the way it's more traditionally written, but really, capital epsilon naught is just equal to epsilon. And it pretty much goes for any equation where you see an epsilon naught. If you throw a dielectric into it, it's now capital epsilon naught. So my capacitance is now double what it used to be. So my capacitance is now that times 2. Do the fancy math there, that's 1.7, 1.77 times 10 to the negative 7 farads. Okay. What you see here? Because we're going to keep manipulating this. All right, so the charge on it, well, my capacitance has doubled, my voltage stays the same because it's still connected to the battery, or power supply, I should say. So my voltage stays the same, my capacitance doubles, so, well, looking at this equation right here, that stays constant, that doubles, what's gonna happen to my charge?
What was the question?
If my voltage stays the same, because it's still connected to the battery, my capacitance doubled, what will happen to the charge?
Bigger,
Pardon?
bigger,
More specifically?
increase.
How much?
Double.
Yeah, it'll double.
Oh,
So my charge is gonna be twice what I had before, which apparently is 2.124 times 10 to the negative 6 coulombs. Let's see, what is the electric field between the plates? Oh, I've got a major equation I can use for that, which is that right there. Why don't we say absolute value of the electric field? Or the electric field strength. What's the electric field strength between the plates? Well, what's the voltage between the plates? I heard it, I think. That's gonna be equal to E times, what's the distance between the plates?
0.01 meters.
So my electric field strength, doing the fancy math there, 1200 what? If someone said something, I haven't heard it yet, so. Be loud, be proud. And maybe be wrong, maybe be right.
Newtons per coulomb.
There we go. Was that loud? I heard it, so I guess it was loud enough.
Mm-hmm.
Were you proud?
Always.
Okay. So now, let's start from scratch. Let's see what we can do with this. Oh, yeah, I meant to ask this question. That was another question I meant to ask. What's the other significance of my giving a distance between these to be 1 centimeter and the plates to be 10 by 10 meters? Ten by 10 meters, so I'm a little under 2 meters tall. So 5 and change of me. And distance between them about like that. What does that allow us to do to make this so much simpler? Louise, you look like you want to say something.
Does it have to do with like the infinite plane thingy, where we can like assume that the charges, that the fields are gonna be pretty.
Yeah, I think you're on the right track there. The wording's a little bit off.
Yeah.
It allows us to make an assumption. So want to fill in the words that Luis was trying to say? Well, looks like they're leaving you high and dry there.
That.
what I think Luis is trying to say. It allows us to make the infinite plate approximation. The fact that the electric field between the two plates, electric,
Right.
the electric field strength is equal to sigma over epsilon sub naught, or over epsilon, which was not more sophisticated. The electric field strength can be approximated by this. Because when we derived this using Gauss's law, we assumed an infinitely large plate with uniform charge distribution. What I'm looking for is the fact that this distance between them is under 10% of the dimensions. And we are considerably under 10%. Allows us making this more accurate. And I think you'll find have you done the Overbeck lab yet? What was the lab we did last week? With the questions? Okay. There's a version of the lab that you will do tomorrow, in which you'll see that actually you can have pretty decent separation and still have that as a decent approximation, but. All right. We'll keep that, I'll make this 100 volts. You know what, we can keep that at 10 and 10. And what I want to know is, I want my charge on the plates doubled, but my electric field strength cut in half. I can, to do this, I can change the dielectric, plate size, distance between plates, voltage, and then I can change connection. In other words, I can connect or disconnect. I'm not necessarily doing all 5 of these, changing all 5 of these things. I can change as many or as few things as possible. If it is not possible, we need to show why it's not possible. This would be a test type problem. All right, so first thing, I want the charge on the plates double, which means my charge has to change. Therefore, I cannot disconnect immediately. As soon as I disconnect, the charge remains fixed. And so I don't want to, so if I'm changing the amount of charge, I have to probably first double the charge before I can even think about disconnecting. I don't necessarily need to disconnect, but find out. Because the distance between them is so significantly smaller than the size of the plate, either dimension of the plate, I can use my infinite plate approximation for my electric field. This would also be equal to the potential divided by B. And so this is the total. If I'm looking at the electric field from just the plates, that would be sigma over epsilon sub naught. Because remember, I build up a charge on the plates, but the dielectric will allow me to increase the charge on the plates, but it has its own I got the two electric fields going on, so there's this electric field right here is from the plates, and that's just sigma over epsilon naught. The total electric field taking the dielectric into account would be just sigma over epsilon. And the difference would be the electric field from the dielectric itself. All right, so first, let me double, what can I do to double the charge on the plates? Similar to the first exercise we did.
Add a dielectric.
All right. What would be the dielectric constant of this dielectric?
2.
All right. So if we add the dielectric of 2, so add dielectric kappa equals 2. Let's see what that's going to do. Let's see, there are other equations we have. We have that the capacitance is equal to Q over delta V. It's also equal to kappa epsilon sub naught A over D. So whatever epsilon naught A over D is, those stay the same, and we're adding the dielectric, we are doubling the capacitance. That would double the capacitance. Why do we know that's going to double the charge?
Because our delta V is fixed.
Yes. So because delta V is fixed, parenthetically, because it's still connected, capacitance is doubled. So